welcome back to another video. Hope everyone's doing well. In this particular video, we're going to go over hypothesis testing, the difference between two means. So if you've seen the video or the lecture on confidence intervals on the difference between two means, this is going to be very similar, just with our added flavor of the hypothesis testing that we've been doing. All right, so what we do is similar to what we did, like I said, with the case with confidence intervals of the difference between two means, is that we're going to compare two different groups. And what we do is we get some sample means and we're going to compare mu1 minus mu2. This is called a two-sample t-test when the groups are independent of each other. Possibly another video, we'll go over what happens if the two samples are dependent of each other. That's called paired samples, and we can get into that in a different video. With this particular video, we're dealing with only independent samples. So what are the necessary conditions? I hope these conditions look very familiar to you. These are central limit theorem conditions. But since we're comparing two different groups, we also have to make sure that the two groups are independent of each other, right? So this is the independent groups assumption. So we need the two groups that we're comparing to be independent of each other, meaning what one group does not affect the other group. And then we need to also check for independence within each of the groups. And how do we do that? It's our good old familiar randomization condition. We check to see if there's some random sampling that was involved. And also we got to make sure that we sample less than 10% of the population. If those are satisfied, then we can say the independence assumption is satisfied. And then for means, right, which means we're dealing with the t-distribution for this one, we also have this nearly normal condition. And once again, I hope this is really familiar. The nearly normal condition says for each sample that we take, if we have a small sample size, and that's generally less than 30, we need to make sure that the data is unimodal and symmetric. Okay, so we need to check that out. But if the sample size is bigger than 30, we can go ahead and ease that condition, and we can continue on, unless the data is really skewed or has outliers. Okay, so less than 30, check the histogram for unimodal and symmetric distribution. If it's bigger than 30, as long as you're not super skewed with a bunch of outliers, you can proceed. All right, so then how do we perform the steps for a hypothesis test for, not proportions, but for two means? For two means. Okay, well, what we're going to do is we're going to write our hypotheses. Okay. Since we're dealing with two different groups here, it's going to be mu1 minus mu2. And we have the usual suspects, right? Our null hypothesis will be the difference of mu1 and mu2 equals 0. And then our alternative hypothesis can take on one of three different categories. It could either be the difference of mu1 and mu2 is greater than 0, right tail test. Mu1 minus mu2 can be less than 0, left tail test, or mu1 minus mu2 cannot equal 0, and that's a two-tailed test. Okay, once again, I'm hoping that after all these videos, you guys are understanding when to use which HA. All right, after you write the hypotheses, we check the conditions, and then here we go, folks. A bunch of formulas. We calculate the test statistic. And how do we get the test statistic? It's x1 bar, so the sample 1 mean, minus x2 bar, so that's the mean of the second sample, and then minus 0. So this 0 is what we call the hypothesized difference, right? And that 0 just comes from the hypothesis here. If for some reason, you won't in this course, but if ever in a different, situation, if you have a different value than 0 here, you would replace in that numerator, you'd replace the 0 with whatever that value would be. But for us, it's going to be 0. And then we divide it by the standard error. Okay? And so the standard error, whenever we're dealing with two different population means, two different groups, and we're working with means, is going to be S1 squared. So the sample standard deviation of group 1, square that up, divide that by N1. N1 is the sample size, sample 1 size. So apologize for not writing that, but N1 is the sample 1 size. And then N2 is the sample 2 size. Right? That makes sense. And then once we have that standard error calculated, we can calculate a t-score. But, and a big but, if you guys recall, when we did the confidence intervals on the difference between two means, remember how we said the degrees of formula has to be a little different? It's this clunky, complicated looking thing. Well, I mean, it's not hard to figure it out, but it's just a little bit tedious. So this is the degrees of freedom formula that you would use if you wanted to do this by hand, but thankfully our technology, whether it be our calculator or something like Excel or StatCrunch that we're going to use, they will do this automatically for us, so we don't have to worry about this. Once we have that test statistic, we can then calculate the p-value. Remember, the p-value is the probability that you get your data given that the null hypothesis is true. Okay? And then once we get that p-value, if the p-value is less than alpha, we'll reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. And those decisions correspond to whenever we reject the null hypothesis, that means there is enough evidence to do so. Whenever we do not reject the null hypothesis, it means there's not enough evidence to reject the null hypothesis. Okay? All right, so I hope that quick little rundown, I hope especially steps, I would say steps 4 through 6 should be very familiar, hopefully, to you guys by now. All right, so we are going to get into an example. All right, so suppose we are interested in knowing if customers at a restaurant tip more on a Saturday night compared to a Friday night. To investigate this claim, we randomly sampled 20 bills at a restaurant on both Friday and Saturday nights. We recorded the tips as a percentage of the total bill. The data can be found in StatCrunch. We're going to let sample 1 represent Friday night, sample 2 represent Saturday night. Using a level of significance of alpha 0.05, determine if patrons tip more on a Saturday night compared to a Friday night. Okay? So, the first thing I like to do is I like to go through and I like to identify what's my sample 1, what represents group 1, and what represents group 2. So we're going to let 1, since they don't tell us explicitly how we should assign them, we're going to let 1 represent Friday night, and 2 is going to represent Saturday night. So keep that in mind. Because we've defined it this way, when we go to write our hypotheses, mu1 represents the mean tip on Friday night, the population mean tip on Friday night. We're going to subtract away mu2, and this is the null hypothesis. So we're saying this difference should equal 0. What that means is that we're assuming that, hey, it's the same amount of tips on Friday night compared to Saturday night. All right, so then now what's our alternative hypothesis? Well, it's mu1 minus mu2. Let's think about this. We're trying to test if people tip more on a Saturday night compared to Friday night. So we're saying if, because remember Friday is the first sample, so we're comparing the mean tips on Friday minus the mean tips on Saturday. So if we're saying that Saturday tips are more, or we're trying to test for that, that means that Friday minus Saturday is going to be a negative number if we're saying that they get more tips on Saturday, right? You have a small number minus a big number, that's going to lead us to something negative. So that's why our alternative hypothesis is 0. Really hope that makes sense to you guys. All right. So that's our hypotheses. Next, let us check some conditions. Okay. So the first condition that we're going to check are independent groups. Okay. And what this means is that the tips that we get on Friday night does not affect the tips that we get on Saturday night. Well, even though we're not explicitly told this, so I think it is very, very reasonable to assume the groups are independent, right? Because that makes sense. What I get on Friday night shouldn't really affect what I get on Saturday night as far as tips, right? Because I have different people coming into the restaurant those 2 different nights, so it should be independent as far as the groups. Now, let's talk about independence within the group. In the group, okay? So in each of the groups, so is there independence amongst all the Saturday tips and independence amongst all the Friday tips? Well, to do that, let's check for our random condition. Did we sample these values randomly? We certainly did. Okay, so we have randomness. We randomly sampled on both days. Also, we need less than 10% sampled. Well, we sampled a total of 20 customers. We got 20 bills. So therefore, yeah, 20 is a lot less than what could potentially happen at that restaurant. Okay, or just in general, people going out and eating. Okay, so yes, we have randomness. We have less than 10% sampled. So independence within the group is satisfied. And we've already previously said independence between the groups is satisfied. Lastly, we need the nearly normal condition. Okay, well, if you recall, we sampled 20. In fact, let's look at the data. So here's the data. Let me scroll up. So the first column are the Friday tips. The second column are the Saturday tips. And so we have a total of 20 data values here, right? So that's a little on the low end. So what we're going to do is let's take a look at the histograms of both of these variables. Okay, so to do that, we go to graph, histogram. Let's look at variable 1 first. Make this just a little bit smaller. All right, and then we go to, I'm gonna go to compute here at the bottom. Not sure if you guys can see it. Let me drag this up. There's our histogram for group 1 for Friday night tips. That certainly looks unimodal and symmetric, right? Certainly. Okay, let's look at group 2. So graph, histogram. Let's grab variable 2. Let's do the same thing. Let's calculate the histogram. Now here the histogram looks a little different, but roughly speaking, right? It doesn't have to be exactly symmetric and unimodal. But here speaking, yeah, it looks pretty unimodal and symmetric, right? So that means when we come back to our nearly normal condition, I would say both histograms are approximately unimodal and symmetric. So because of that, we have our nearly normal condition satisfied. All right, so those are the conditions. Let's keep it moving. Next, let's calculate the test statistic and the p-value. Okay, well, what we're going to do here is we're going to do all this in StatCrunch. We're not going to do this by hand. So let's go to StatCrunch. Let me clear out my graphs here. And this is what we're going to do. So we are doing a two sample test on the means. I'm trying to get it to zoom out here. There we go. All right, so we go to stat and we go to t-stats. We're dealing with the mean. We go to t-stats and we go to two sample. Okay, so in our particular example, and this is the only example I'll do in this video, is we have the data. But let's quickly look at what happened if we didn't have the data, but they gave us the summary information. What I mean by that is they told us the mean of the Friday tips and the standard deviation of Friday tips, and same for Saturday, as opposed to the data set. So let's look at that really quickly. And you'll see here it doesn't ask for anything egregious, right? We need to give it the sample mean for group 1, the sample standard deviation for group 1, and they want to know the sample size for group 1, and then repeat the same thing for group 2. The mean for group 2, the standard deviation for group 2, and the sample size for group 2. And then, okay, this pool variances. We are not going to pool variances for this. I know we've talked about pooling a little bit in this course, but never pool variances. It's okay to not pool the variances. And then we're going to perform a hypothesis test, and then we put in the correct value. So if you have just the data, they give you just the sample standard deviation and the mean and stuff, this is where you would go. Excuse me, if you had just the summary statistics. But for us, we have the actual data. So when we go back to stat, t-stats, and to sample, we're going to go to with data. Okay. And so now what do we put in? So first of all, they want to know about sample 1. Where are the values located in sample 1? Well, they are located in the variable 1 column because we said Friday tips were sample 1. And in fact, what I should probably do here, so let me do this. Let me clear this out because that might mess up our data. Okay, these are actually the titles. So let's do this. Let me go up here. Let me rename this as Friday tips. And then let's rename this one as Saturday tips. All right. That should work. Okay. All right. So then let's go back. So if we have it labeled that way, then when we go under values, there we go. Now the name pops up. So Friday tips, and then that's sample 1, and then sample 2 would be Saturday tips. Okay. Let me see. That should be it. And then we go down here. Like I said, don't worry about pooling. And we go down to hypothesis test. We're doing mu1 minus mu2 equals 0. And then remember, we're testing if the Friday tips, which is group 1, minus the Saturday tips, we're trying to see if Saturday tips are more. So that means that this difference, the way that we define it, has to be negative, less than 0. All right. Now we go down to compute. Oops. And there we go. There's all of our information for our test, our hypothesis test. Okay, so they gave us the standard error. They did that nasty degrees of freedom formula for us. That's the DF. And they give us a t-stat and a p-value. So let's write that down. So our test statistic is a 0.575. That's the t-stat. So let's write that down. So t-test, the test statistic is a 0.575. And the p-value is equal to 0.716 if we go to 3 decimal places. All right, which is a relatively large p-value. Remember, p-values go between 0 and 1. So what does it mean that a p-value is 0.716? It means that it's pretty likely, given that our null hypothesis is true, that we observed the data that we got. So the higher the p-value, the more usual or the more likely our data becomes. Right? The smaller the p-value, the more unusual it becomes, and that's why we reject the null hypothesis. But we've discussed that in the past. You guys should be good. All right. So now we need to compare our p-value of 0.716 to our alpha level of significance. So we take 0.716, we compare it to alpha, which is 0.05. So this is alpha, this is the p-value. And so we've kind of already discussed this, but the p-value is greater than alpha. 716 is greater than 50, right? So therefore, we should not reject the null hypothesis. So do not, or fail, whatever you want to say, do not reject the null hypothesis. Okay, which means there is not enough evidence, or there is not sufficient evidence to state that the population mean tip on Saturday is more than the population mean tip on Friday. Okay, so what that means is that we got this value here, and it's just not enough evidence to say that people tip more on Saturday when compared to Friday. All right, so the moral of the story here, folks, is make sure you correctly label your samples 1 and 2, and then use technology. Do not use these formulas, but I hope the formulas do provide some intuition on how we calculate these values. All right, I appreciate you guys as always. I hope to see you in the next video. Take care.